In this video I want to share with you the working principle of DC to DC regulators and converters, or as some people know it, DC to DC converter circuit. Since it is highly effective and cheap, it is very popular nowadays.So. I want to teach you its working principles in a simple way, and I hope this experience may be helpful to you as well. In some parts, may not be in accordance with academic principles. But let's just understand the general principles first. Then we'll go into more detail later. Switching power supplies offer higher efficiency than traditional linear power supplies. They can step up, step down, and invert. Some designs can isolate output voltage from the input. This video outlines the different types of switching regulators used in DC-DC conversion. It also reviews and compares the various control techniques for these converters. What are the fundamentals of switching power supplies? By definition, a switch-mode power supply, SMPS, is a type of power supply that uses semiconductor switching techniques, rather than standard linear methods to provide the required output voltage. The basic switching converter consists of a power switching stage and a control circuit. The power switching stage performs the power conversion from the circuit's input voltage, VIN, to its output voltage, VOUT, which includes output filtering. The major advantage of the switch-mode power supply is its higher efficiency compared to standard linear regulators, and this is achieved by internally switching a transistor, or power MOSFET, between its ON state, saturated, and its OFF state, cutoff, both of which produces lower power dissipation. This means that when the switching transistor is fully ON and conducting current, the voltage drop across it is at its minimal value, and when the transistor is fully OFF there is no current flow through it. So the transistor is acting like an ideal ON/OFF switch. Unlike linear regulators, which only offer step-down voltage regulation, a switch-mode power supply can provide step-down, step-up, and negation of the input voltage using one or more of the three basic switch-mode circuit topologies: buck, boost, and buck boost. These names refer to how the transistor switch, inductor, and smoothing capacitor are connected together within the basic SMPS circuit. Buck switch mode power supply. First, the VIN charges the C1 capacitor until it is full. So, its voltage is the same as that of the power supply, VIN. The switch, S1, turns on, closing the circuit. It causes the positive voltage to flow into the circuit. This positive voltage drops across the coil, L1, because now the VIN is greater than the Vout. The current flow through the coil increases at a linear rate. So, there is energy stored in the coil, L1, and an electromagnetic field radiates from it. But no current flows through D1 because now it is reverse biased. And when L1 reaches its saturation point, the current will flow through it like a normal conductor. So it can charge C2 until it is full as well. S1 turns off or opens the circuit, causing no electrical energy to flow into L1 anymore. But the electromagnetic field around it began to collapse, causing an induction and releasing an electric current in the alternated polarity from the original. The D1 is now forward biased, so the L1 current can flow through D1 to GND. Now that L1 and C2 are parallel, the L1 currents add up to the energy already stored in the output capacitor C2. This causes the current at Vout to increase for a moment. However, the current at the coil decreases linearly until it is re-energized by the Vin again. So as the switch S1 turns on or closes the circuit, it causes the positive current to flow into the circuit again. The whole process is the same. This whole process causes the output voltage level to be constant and able to supply the load continuously. Does it start to get complicated? See the simpler power supply circuit. The big problem is the difficulty in controlling the switch S in a way that will give us a higher current at the output. There are three modes of current that flow through L1, as shown in the graph. "5 volts buck converter circuit using transistors." Now that we know the basics, we can build a real buck converter circuit. We are going to use the series voltage regulator as a base and build off from there. In this video, you can learn more about series voltage regulators. The main change we made was adding the inductor L1. It works as an excellent electrical energy storage tank, similar to a capacitor. You can learn more in this video. Another component of note is Q1, which acts as a switching unit that works with L1, D1, and Q2 transistors. Both NPN, Q2, and PNP, Q1 transistors will feed back each other to continuously switch and generate a frequency. When we apply electricity to the circuit, Q2 will work. Because a base current flows through R1 to bias Q2 into the conducting state. As a result, the positive current flows through pin E to pin B of Q1 and flows through CE of Q2 to the GND. In this case, it means that Q2 is used as Q1's bias controller so that Q1 can supply a high current through pin C to coil L1. The pin B of Q2 is also connected to pin C of Q3, which has ZD1 and R4 connected to pin B to control the voltage to be approximately 5.2 volts. The way it can achieve this is when the output voltage level exceeds 5.2 V, the current will flow through ZD1 to pin B of Q3, causing it to conduct current between its C and E pins. Functioning like a closed switch, giving the current a shorter path through pins B and E of Q2. As a result, Q2 stops conducting current, and so does Q1, and the output voltage drops. Now coil L1 will start releasing the current, and D1, which acts as a rectifier, will rectify the negative potential and then charge up C2 through its negative polarity. Until L1 runs out of current, the cycle will start over again. Adjustable buck switching voltage regulators. A voltage regulator maintains a constant output voltage for a circuit, regardless of any changes in connected devices or electrical load. A switching regulator is a voltage regulator that uses a switching element to transform the incoming power supply into a pulsed voltage, which is then smoothed using capacitors, inductors, and other elements. This circuit achieving efficiencies surpassing 80% and outperforms linear regulators, which generally exhibit maximum efficiencies ranging from 33% to 42%. The circuit consists of several parts that I will explain each part separately for better understanding. Astable multivibrator and pulse generation. The operation commences with transistors Q1 and Q2 configured in an astable multivibrator arrangement. This configuration yields a brief positive pulse at the base of Q3 at intervals of 50 microseconds. Consequently, the capacitor C4 discharges, subsequently recharging through the R7 resistor. This process delivers a gradually ascending voltage to the base of Q6. In this video, you can learn more about multivibrators, voltage comparison and regulation. Transistors Q9 and Q10 undertake a voltage comparison task, juxtaposing the reference voltage from the ZD2 with a segment of the regulator's output voltage. This voltage slice derives from a potentiometer serving as the output voltage adjustment feature. In these videos, you can learn more about voltage comparisons and regulation. Adjustable voltage control and pulse width modulation. As the potentiometer pin 2 voltage exceeds the reference voltage, Q8 activates. Consequently, the ascending ramp at the base of Q6 must escalate to align with the voltage at the base of Q7. This delay in activating the Darlington pair, Q4 and Q5, results in a narrower power output pulse to the inductor. This mechanism, known as pulse width modulation, PWM, in turn reduces the output voltage. The nominal operating frequency is 20 kHz, although it can vary considerably due to input voltage fluctuations. Output stage and energy dissipation. The D1 diode is specified for the catch diode, but in the prototype, a high current rectifier proved effective. The frequency of 20 kHz seems manageable for these components. The output voltage feedback attenuator incorporates 50 ohms resistors to draw a minimum of 50 mA from the output, essential for maintaining stability. What is a boost converter? To understand the working of a boost converter, it is mandatory that you know how inductors, transistors, diodes, and capacitors work. With that knowledge, we can go through the working of the boost converter step by step. A boost converter is one of the simplest types of switch mode converter. As the name suggests, it takes an input voltage and boosts or increases it. All it consists of is an inductor, a switch transistor BJT or MOSFET. These days it's a MOSFET, since you can get really nice ones these days, a diode, and a capacitor. Also needed is a source of a periodic square wave. This can be something as simple as a 555 timer or even a dedicated SMPS IC like the famous MC3463A IC. They're so simple because they were originally developed in the 1960s to power the electronic systems on aircraft. It was a requirement that these converters be as compact and as efficient as possible. The biggest advantage boost converters offer is their high efficiency. Some of them can even go up to 99%. In other words, 99% of the input energy is converted to useful output energy, only 1% is wasted. How does a boost converter work? Now with this knowledge, we can go through the working of the boost converter step by step. Step 1. Here, nothing happens. The output capacitor is charged to the input voltage -1 diode drop. Step 2. Now, it's time to turn the switch on. Our signal source goes high, turning on the MOSFET. All the current is diverted through to the MOSFET through the inductor. Note that the output capacitor stays charged since it can't discharge through the now back-biased diode. The power source isn't immediately short-circuited, of course, since the inductor makes the current ramp up relatively slowly. Also, a magnetic field builds up around the inductor. Note the polarity of the voltage applied across the inductor. Step 3. The MOSFET is turned off and the current to the inductor is stopped abruptly. The very nature of an inductor is to maintain smooth current flow. It doesn't like sudden changes in current. So it does not like the sudden turning off of the current. It responds to this by generating a large voltage with the opposite polarity of the voltage originally supplied to it, using the energy stored in the magnetic field to maintain that current flow. If we forget the rest of the circuit elements and notice only the polarity symbols, we notice that the inductor now acts like a voltage source in series with the supply voltage. This means that the anode of the diode is now at a higher voltage than the cathode. Remember, the cap was already charged to supply voltage in the beginning and is forward biased. The output capacitor is now charged to a higher voltage than before, which means that we have successfully stepped up a low DC voltage to a higher one. I recommend that you go through the steps once again very slowly and understand them intuitively. These steps happen many thousands of times, depending on the frequency of the oscillator, to maintain the output voltage under load. Boost converter circuit using 555 timer IC. In this tutorial, we are going to make a boost converter circuit 555. We've all come across pesky situations where we need a slightly higher voltage than our power supplies can provide. We need 12 volts but have only a 9-volt battery. Or maybe we have a 3.3 volt supply when our chip needs 5 volts. That too, in most cases, the current draw is quite decent. We can achieve it by boosting the converter. A boost converter is a DC to DC power converter that steps up voltage while stepping down current from its input supply to its output load. Working explanation. As we can see in the circuit, timer IC 555 is configured in astable multivibrator mode. The output pulse from the timer IC is applied to the Q1 transistor base. Here Q1 acts as a switch. The collector terminal of Q1 is connected to the positive power supply through inductor L1, and the emitter terminal is connected to the negative supply. IC 555 astable multivibrator mode produces continuous pulse output. We can increase or decrease the output pulse frequency by changing the value of an RV1 variable resistor. Now the boosted output voltage is taken from the L1 and Q1 meeting point and then rectified by the diode D1. C3 capacitor removes ripples and noise from the output voltage. Circuit of boost switching regulator, adjustable. Most of you familiar with this DC to DC boost converter board. The boost converter board can able to provide up to 35 volts DC in the output, 12 volts to 35 volts. So in this video would like to share the schematics of this DC to DC boost converter and explaining about how it is working. The boost converter is working with UC3843 IC. The input voltage of this circuit is 9 volts to 35 volts DC, means if you applied pulse on the input section you can get up to 35 volts DC with 6 amps current. You can see more specifications of this circuit. Working explanation. The UC3843 is a popular IC using in SMPS circuits. The IC is built with a pulse width modulation circuit to control output voltage of the power supplies. C1 and C2 have been used to reduce the input noises. L1, D1, and Q1 build a boost conversion network. L1 is an 10A 100 microhenries inductor. D1 is a Schottky diode, 2 parallel diodes in one package. Q1 is the IRFZ 44 N-channel MOSFET. The ON resistance, RDS-ON, of the MOSFET is just around 28 milliohm and it can handle up to 50A. C8, C9, and C10 are used to reduce the output noise. Usually, a boost converter output is noisier than a buck converter, especially by using discrete components. A single-chip buck boost controller is less noisy, however, the output voltage and current of these controllers are limited. So, these characteristics make these components a good fit for this project. The internal structure of IC-UC3843 consists of oscillator, error amplifier, PWM comparator, feedback loop circuit. The oscillator circuit inside of the IC will produce the sawtooth waveform at a high frequency. The frequency is determined by the externally connected components to the circuit. The error amplifier will cross-check the reference voltage applied through the voltage regulator and output voltage of the power supply. Then it will produce the error signal on it. The PWM comparator receiving this error signal and it will compare the error signal with the sawtooth waveform. Depending on this comparison, the circuit will turn on and off at a particular cycle. As a switched mode powering, the output signal is taking out from the pin number 3 of the IC to drive the power MOSFET. R1 is a 10-cohm multi-turn potentiometer that you can set to adjust the output voltage. R10 and R11 have been placed in parallel that builds a preliminary load to help to stabilize the output voltage.